So today we'll talk about coordinate descent. And this is part of your homework, coordinate descent algorithm. It's part of your homework. I don't know if you guys started your homework. I'm hoping you guys at least took a look at it. And I hope it's shaping up to be not too terrible and educational as you guys work through it. I will probably get homework 5 posted up sometime later today, and the reason why I want to get it posted up now is because I want to give you guys as much time as possible to work on it. It is a little bit of a tougher assignment, kind of like the tic-tac-toe, but maybe even harder. And so what you're going to do on this one, it's because we're going to get into this idea of simulation as a way for doing computational statistics. And so sometimes you cannot answer questions directly based on the math, or the math, it gets really complicated. And so simulations are the way to go. And so what you will be doing is you'll be simulating board movement on the game Monopoly. Okay, and I'll detail everything out. We'll talk probably about it a little bit more on Wednesday, and I'm also going to provide you some code to get you started, because in the past I didn't do that, and then students were overwhelmed by the task. So I'm going to give you some code to get you guys started, and I'm hoping that makes it a little bit easier. But we'll talk about it on Wednesday, okay? But you can look at that and just start thinking. And if you've never played Monopoly, then it would be a good time to watch some videos, or find some friends who are willing to throw 4 hours down the tube. I don't know. It's like an American classic that you all play at family time at Thanksgiving and then get in a fight later about. It's not Thanksgiving without a fight over Monopoly. Okay. Coordinate descent. Okay, so coordinate descent is a multi-dimensional optimization algorithm. Okay. So on Friday we talked about unidimensional optimization algorithms, and there are many, and we just talked about a few of them, right? We talked about Newton's method for optimization and the golden section search for optimization for unidimensional functions. Okay, what coordinate descent does is it takes a multidimensional optimization problem and it basically breaks it down into a series of unidimensional optimization problems. Okay, so coordinate descent will turns a multi-dimensional problem into a few unidimensional problems. Okay, and so imagine we've got so here we've got a function of x and y, so this is a two-dimensional problem, and forgive my drawing here, this is supposed to be, don't laugh, okay, all right, so this is, this is like a bowl, okay, and or what are you, paraboloid, is that what it's called? Okay, and then you're trying to find the minimum here, right? And so, if we make a contour plot, look, this one is I don't know what this is. Okay. I don't know how this works. Okay, so we have something like this, okay? And the way coordinate descent works is, you start off with some initial point here, okay? And you get, this is your x0 and your y0. And what you're going to do is you're going to search along, you're going to say set y equal to y0, okay? And so your function, so here's the algorithm. You have f of x and y, and basically you set y equal to y0. And when you do this, f of x y, where y is equal to y0, becomes just a function of x. Okay, and we might say f of x, where y is equal to y0, this just becomes a function of x. So this becomes a unidimensional problem, right? Becomes a unidimensional function. Okay, actually let me just slide this down. Okay. And so it becomes a unidimensional problem, and you're going to find the value of x that minimizes this function, f where y is equal to y0, f of x, okay? And then you would use that, okay, set the next one to be the value of x. And then so now we have we update the function and we say f of x and y, where x is equal to x1. This is now just a function of y, right? So now we have a new value of x, and we're going to say, okay, we're going to set the function here. So this is going to be my value x1, and I'm going to find the value of y that minimizes this, okay? And in this case, we got to, we'll get to our center very quickly, okay? And then so now we find the value of y. Find the value of y that minimizes this function, f of y. All right, so you've got multiple variables. You're going to set all of them equal to a constant, and if all of the other ones are constants, then it becomes just a function of one variable. And then you just go back, you just iterate, going through each variable one at a time, finding the value of x that minimizes the function of x, and finding the value of y that minimizes the function of y. And then you iterate. Okay, and so in this example, it hones in quickly. In other examples, I think we have something, wait, how do I do this? Okay, wait, don't draw this on your paper yet, because I'm gonna turn the angle on this. I think I can do this, right? Okay, so you might have some function that looks like this. And again, you start off with some point here, and what this is going to look like is what's going on? You set y equal to some value y0, and you say, oh, it's going to get minimized, I don't know, right here, okay? So then you set x equal to this, and you say, oh, it gets minimized right here, okay? And so for this, we say x is equal to, x1, and then you just keep going back and forth, and you say, and we find, y is equal to y1, and you just keep iterating back and forth. X equal to x2, and here eventually you're going to kind of just get this, zigzag pattern. Okay, and so coordinate descent often forms these little zigzag patterns to get to the optimal value here. Yes?
So what you're doing, just so I understand what you're saying, so you set y equal to y naught, and then you find the x that minimizes the function at that slice of
yes,
y,
yes.
and then you just keep on.
Yes, that's exactly what we're doing. It's called a line search, okay? And so let's say we have f of x, y. Let's say this is, I don't know, 2x squared plus 3xy plus 4y squared, or something like that, okay? So basically, let's say, y is equal to y0. We're going to set y equal to y0. And let's say y0 is equal to, well, just for simplicity, let's say y0 is equal to 0, okay? So what this becomes is that you've got f of x and y, but you're going to set y equal to 0. And this basically just boils down to 2x squared, okay? And this is a dumb problem now, but okay. And then so now we find, what is the value that's going to minimize this, right? What value? What value minimizes this, okay? And then we would say, oh, okay, x is equal to 0, okay? This is going to minimize this. And then so now you get f of xy, where x is now equal to 0. And, okay, so this is stupid. And this boils down to 4y squared. Okay, and what value minimizes this? And this is going to be y equal to 0. So this was not a good example. But, let's say you started off at, this was a bad example, I apologize. Okay, but basically you're just taking it, you find the value that minimizes the function after you plug it in, and then you find the value of the function, and then you plug it in there, okay? Now in R, it's nice because R has these scoping rules, right? So you can set x is equal to, let's say 5, and then you say y is equal, set that equal to 5 also, or something, right? And then you're gonna have f as a function of x, all right? And you say f as a function of x is equal to, you just do 2 times x squared plus 3 times x times y plus 4 times y squared, okay? And because of our scoping rules, you can plug in the value of x in this function, and it's going to give you the correct value. But because it doesn't have an actual value of y, the scoping rule will take the current estimate of y. Okay? So we can, it'll take the current estimate of y, and then likewise you create f as a function of y, and you have pretty much the exact same thing. And the only difference is that this is a function of y, so it's going to plug in the values of y here. But, you know, the scoping rules will tell it to search the environment for the variable that it doesn't have, right? So R's scoping rules tell the function to search the environment. So here you can plug in, you know, 10 for x, and it will plug in 10 where it says x, but then where it says y, it's going to search the environment for 5. Okay? Over here you can plug in 20 for y, and it will plug in 20 where it says y, but then it'll look at the environment and say, oh, x is equal to 5 in the environment. Okay? And so that's a nice thing of our scoping rules, is that you can kind of leave these variables in place in the function, and you define the function as a function of x or a function of y, and the thing that it doesn't have, it's going to search the environment to plug in those. Okay? And so here's here's an application for maximum likelihood. So we can use coordinate descent for maximum likelihood. Okay, so let's say we have, you know, some normal distribution, okay, and so this normal distribution is a function of mu and sigma, okay, and let's say we've just generated a bunch of data, okay. So what is the likelihood of our data? Okay. The likelihood of our data will be, we're going to have to find, it's going to be the product, assuming everything is independent of each other. This crossing the axis is bothering me. So it's going to be the product, right? We're going to multiply, and what do we multiply? The probability of each individual data point. Yeah. Okay. So what's the probability of each individual data point when it's? Huh? It's that the normal distribution, right? You look up normal distribution, and you go, you go to Wikipedia, and it's this. What is it? It's this thing, right? It's the PDF of the normal distribution, right? It's 1 over 2 sigma squared pi e to the x minus mu squared over 2 sigma squared, right? So that's what it is. In R, we have a function that gives this value to us, so we don't have to type in all of this in. What is that? What function in R gives us the probability? Not p-norm. P-norm gives us the cumulative density, right? P-norm will give you the area to the right of a certain x, right? So if you want the probability or the density of that individual x, what do we use? D-norm, right? D-norm. D-norm is for the density of the point that we want, right? So, you do D-norm of your x value with mean equal to something, and, mean equal to mu. Mu hat, right? So you have estimates, mu hat, and sigma hat. Okay, so you say mean is equal to mu and standard deviation is equal to, sigma hat, right? And then, x will be your data. So you give it a vector of this, of your data points, and then you do the product of all of this, right? And then this would be the likelihood. Is that okay? So we could tell R, give me the product of all of my D-norm values. the only problem here, okay, so mathematically this is totally fine, okay, there's no problem here. However, from a computational standpoint, we run into problems because let's say the true value, the true value of our thing, the mean is at 100, okay, but our current estimate is at 0, right? And let's say we have a standard deviation of 1, okay, so we are 100 standard deviations away from the thing. Computationally, this is going to be 0, right? Because we have a finite number of things. We're not able to represent values that small, okay? So if we just use plain old d norm, it's going to be like 1e to the negative 100 or something, and maybe it can distinguish, but we're going to run into problems with things that are super incredibly small. So it's better for us if we use the log of the probability, okay? So rather than having a tiny, a number very close to 0, we would just have a very negative number, okay? So we will use the log likelihood to avoid, the numeric problems of having values super close to 0, okay? The computer numeric problems. Okay. So when you take the log of this becomes the sum of basically, and it's going to be d norm x mean is equal to mu hat, standard deviation is equal to sigma hat, and what you do is you say log is equal to true. Okay, and so this becomes the log likelihood, and it's going to be the sum of this. And we can, if we maximize the log likelihood, it will maximize the actual likelihood because the log is what we call a monotonic function, meaning it's always has a positive slope, so that if you maximize the log, it's the maximum of the log likelihood is the maximum of the actual likelihood, okay? So the log is a monotonic function, which means it's always increasing. There's no spot in the log function where it has a negative slope, okay? So the max of log likelihood will be the max of the actual likelihood. Yes?
Why would it be sum there and not product?
Hang on a second. It's a sum and not the product because the log of a product is the sum of the logs. Right? The log of a times b is the a plus log of a plus the log of b. So it's just a little trick that we do. Okay. Okay. So I've implemented this in my R code. So let me clear out my environment also. We'll delete all of this. Okay. So here I'm gonna just load up my golden function. Okay, golden just does a unidimensional optimization. Okay, and here I'm gonna generate a bunch of normal points. Okay, so here, let's say, all right, we'll just do this. I've got 1,000 data points, and if I do histogram of my data, okay, it looks like this. All right, so 1,000 data points, mean is 900, standard deviation of 5. Okay, no problem there. Okay, we're going to start off with a current estimate of mu at 0 and a current estimate of sigma at 1. Okay, so these are just terrible estimates of what the data is. Okay, and this is going to be the log likelihood. Okay, what we want is the maximum likelihood, and so instead of maximizing the likelihood, we're going to minimize negative of the likelihood. That's all we're doing. Okay, okay, and so the likelihood is I'm taking d norm, which gives me the density of each data point, right? So if I did d norm, if I say mu is 0 and sigma is 1, and if I just said, what is d norm of, I'll just show you, okay, d norm of, let's say 900, which might be one of my values, using a mean of equal to 0 and standard deviation equal to 1, okay? Okay, so that says it's 0. Let's try log is equal to true, okay? And it's so you can see the difference between using the d norm. D norm says the probability of this happening is 0, but it's not actually 0. It's just something very close to 0, and it just has a, you know, it's e to the negative 5,000. Okay, so the log likelihood will just give us a very negative number rather than a number that says 0, right? Okay, because instead of you know, so at 90, you know, if I'm 90 standard deviations away, my log likelihood is only negative 4,000. Whereas if I didn't have log equal to true, this might also just say 0. Okay, so this is why we're using the log likelihood, because the regular old just asking what's the probability density at this point, R is telling me it's 0 in both cases, but it's not, and one is much more unlikely than the other, right? 900 is far more unlikely than 90 if the mean is 0. They're both incredibly unlikely. One is 90 standard deviations away, and the other is 900 standard deviations away. It is lost if we just ask for the regular old density. So this is why we're using the log density. Okay, and we do this, and we do this for all of our data points, and we're going to add them up, and we're going to multiply by -1 because we want to minimize rather than maximize. Okay, and so here, I just want you to look at the way this function is written. This is likelihood as a function of mu. Okay, and I'm saying it's a function of x, and x gets put into where mu goes, where the mean goes. Okay, and here it says sigma, so sigma is going to get drawn from the environment. Okay, likelihood as a function of sigma is a function of x. Mu is going to come from the environment, and whatever our estimate of x goes will get plugged into here for where the standard deviation is. Okay, data again is also coming from the environment. So these are just both functions. The inside of this is pretty much the same. It's just telling them where to draw the thing. So the thing that this is a function of x, meaning we're going to modify the mean, and over here we're going to modify the standard deviation. Okay, so here I've got the likelihood as a function of mu, likelihood as a function of sigma. Okay, so currently my estimate of mu is 0, my estimate of sigma is 1. These are both terrible estimates, and all I have to do is I'll just do one iteration right now. I'm going to say take a golden section search function and find the value that will minimize this thing, which basically finds a value that maximizes my likelihood as a function of mu. Okay, and we're going to search on the range -1,000 to 1,000. I tell it to do it, and it says, oh look, the value I decided to go to is 899.94. Okay, and so if I run that, I'm going to update my mu. My mu is now 899. Okay, now that I've done this, I'm going to run golden section search using this new value of 899. That's going to go into my sigma, and it's going to say, give me the value of sigma that maximizes or minimizes the inverse of this, and it says, oh, okay, the value there is 5.171. Okay, and basically I just do this back and forth. I just do this over and over and over again, and here I've done 10 iterations. It went really quick, and it has settled on an estimate of mu of 899.94 and an estimate of sigma of 5.177. Okay, which aligns very closely to the original values of mean and sigma, or mean and standard deviation that I used to generate the data. And in fact, if we ask, what is the current mean of my data? The mean of my data is my maximum likelihood estimate. Okay, so the maximum likelihood estimate actually is the mean of my data. And then if I ask the standard deviation of my data, it's very close. And I think probably in 100B you learned that the standard deviation of your data is not going to be the maximum likelihood estimate of the standard deviation, or maybe you learned that, maybe you didn't. And so we have that, right? And you know, I can change this. I could change my mean to 90 and my standard deviation to be 50. Okay, and I can generate new data, reset my mu and sigma to be 0 and 1. And again, I just run through the loop, and now it has updated my estimate of mu to be 89.417. My estimate of sigma is 51.71, which is pretty close to the values I used. And we can just check, you know, what's the mean of my data? It is that, and then the standard deviation of my data is quite close to what my maximum likelihood estimates are settling on. Okay. The normal model problem here. This is an example where the coordinate descent converges very quickly. Okay, and it's the circles or the contour of different values of mu and different values of sigma look kind of like this, and it's like after 2 iterations it's going to kind of settle on almost the exact values very quickly. Okay. Let me show you an example where it's a lot more jagged, and it's going to take a lot more iterations to get to the actual value. Okay. Well, before I go on, are there any questions on how this coordinate descent algorithm is working? Yeah.
Can you explain again what answer the maximum likelihood, like as a concept, tries to answer?
So maximum likelihood, it's trying to find the values of, in our situation, right, we're saying our data is coming from the normal distribution. The normal distribution is defined by the mean and standard deviation. And we want to find the mean and standard deviation that's going to maximize the likelihood of our data. So we have data, you know, we got 1,000 points of data that's coming from some unknown normal distribution. Okay? And we're going to say, what if I said the mean is 50 and the standard deviation is 10, what is the likelihood of observing this data? I can do that by finding the likelihood of each individual data point and multiplying the product together. Okay? And mathematically that's fine. Computationally we run into problems because we get values close to 0. So we do the log likelihood instead. But again, we're just trying to find the estimates of our parameters that will maximize the probability of observing our data.
Okay.
Okay? Yes?
Can you go through the for loop again and explain like the values that are being used?
Yeah, so in my for loop, I'm just saying do a golden section search on the function likelihood as a function of mu. Okay? So I've turned my likelihood function, which is truly a function of 2 variables, mean and standard deviation. I've turned them into just functions of 1 variable. I said hold the standard deviation constant to be equal to sigma, but vary x. Okay? And that's what likelihood mu is. It's the likelihood function where I'm varying x, which is the mean. Vary the mean, hold the standard deviation constant, find the value of the mean that's going to maximize this thing. That's what this first one does.
And when you said use the constant, it's searching in the global.
Yeah, so in the global environment, I'm saying currently my estimate of sigma is 1. Using my estimate of sigma 1, okay, change your values of the mean mu to give me the value that's going to maximize it. Okay? And over here, we're doing just the opposite. Hold the mean constant, vary the values of sigma. Find the one that's going to maximize. Yeah?
And the golden function just does like the golden optimization method that we went through.
Yeah, so, yeah, it's the exact function that so this is not using some kind of R internal optimization. It's the golden function that I taught you guys on Friday, which says, you know, start with a lower bound, an upper bound, use the golden ratio to get an x1 and an x2, compare those values, and then, you know, discard a section of the thing, and, you know, keep repeating that until you zero in on a spot. Okay, so that's what we do, and we're iterating. Yeah.
How did you know to do 10 iterations for the loop?
I didn't. Well, here I just did 10 iterations. This was an example where, you know, I could have just done 2 iterations and our estimates would have been like just as good. Okay, the normal doing maximum likelihood for the normal distribution is an example where the coordinate descent algorithm works very, very, very well. It works very quickly. It'll converge after maybe 2 or 3 iterations. Okay, here's an example where it doesn't converge. Okay, so this is linear regression, right? So in linear regression, what are we trying to minimize? Yeah, we're trying to minimize the sum of squares residuals, right? So here I'm going to just generate some random data, okay? Here, we're going to random x's, random y's. I'm doing y is negative 400, my intercept is negative 400 plus 8, so my slope is 8, and I'm just adding some noise, okay? And so when I do this, this is what my plot looks like, and we want to find the function here that does this. According to this, the least squares line will have an intercept of negative 400.389 and a slope of 7.989. Okay, so in this case, this is that, and here we can write the function that we want to minimize, right? We want to minimize the sum of squares. Okay, and so if we think about what sum of squares residuals is, first we got to find y hat. Y hat is going to be intercept plus slope times x. The residuals are the difference between our data values y and y hat, y minus y hat. Those are my residuals, and the sum of squares residuals will be the sum of those residuals squared. Okay, and so SSR slope, it will take our current estimate, it will vary the slope, and it will return the sum of squares residuals value. Okay. Over here I've got SSR intercept. The insides are exactly the same, but over here the only difference is that this is a function of the intercept and not a function of the slope. Is that clear what's going on there? So it's the same thing. We're just saying calculate the sum of squares as a function of the slope. Over here, calculate the sum of squares as a function of the intercept. Where in reality, the sum of squares is a function of both of those things, right? You plug in your intercept and you plug in your slope value and you're getting something back. Okay, and so here I'm going to plug this in, and here we can see that the coordinate descent algorithm doesn't work as well. Okay, so currently my estimate of the slope is 0 and my estimate of the intercept is 0. I'm going to say use the golden section search the range negative 100 to 100 and give me the value of the slope that's going to minimize the sum of squares residuals. Okay, and right there it says, okay, my updated slope is 2.3. Okay, reality it's closer to 8. Okay, I can say, okay, well, update the slope to that. Now using that, update the intercept. Okay, and it says, okay, well, my updated intercept is going to be negative 0.58. Okay, so these are far cries from what their actual values are. Okay, but I can try this again. I can say, okay, well, take that value of the intercept. What is my new value of the slope? Okay, 2.312. Okay, it's getting a little bit closer. What's the value of the intercept? Okay, it's now at negative 1.16. Okay, and so we can see it's getting a little bit closer, but it's moving a lot slower. Okay, so here I'm going to just try 50 iterations. Okay, after 50 iterations, what's the value of my slope? It's at 2.71. What's the value of my intercept? It's at negative 29. Okay, and this is an example where I need lots of iterations. So let's do 1,000 iterations. Okay, after 1,000 iterations, my slope estimate is at 6.75, and my intercept estimate is at negative 313. This is still pretty far off, okay? I'll do another 5,000 iterations. Okay, it takes a little bit longer to run now. And we're going to see we're getting a little bit closer, okay? Slope is 7.988, and the intercept is negative 400. Whereas if we look at our model, model $ coefficients, the actual values are negative 400.388 and 7.989. Okay, so we're getting very close, but it's not quite there. So if I run another 5,000 iterations, you know, we'll see our values do get a little bit closer. Okay, this is pretty close. Okay, and the value of my intercept, okay, is also pretty close. But this was after like 10,000, 11,000 iterations. Okay, so you can imagine, you know, the contour of this thing is just it's just this very narrow and very extreme thing where it's going to have to do like thousands of these little zigzag things. Okay, so in certain applications, just the way the contour is set up, coordinate descent runs into problems. Okay, trying to you know, it's zigzagging a whole bunch, and it's having problems. Not having problems, but it's just slow to converge. Okay, and in other applications like the maximum likelihood, if you just try it out and just do a couple iterations on your own, you'll see it converges almost instantly after maybe 2 iterations. Okay, this one took 10,000, 11,000 iterations, and we're still not quite converged. This the other one, it converged maybe after two iterations. And so so that's coordinate descent. It basically takes the multidimensional problem and it reduces it into a series of unidimensional problems to try to solve it. And there are certain cases where if you have this really awkward shaped contour thing or awkward shaped surface, then coordinate descent can fail. But in many cases it is pretty good at finding where it needs to go. Okay. All right. We'll end there. We'll see you guys on Wednesday. Have a good day and go out there and vote.